Okay, with this vector word problem, we have a game of tug of war, or a game of strength, they call it. So there's three teams, A, B, and C. And as you read through this, they're all pulling in their own direction, but the thing that makes this an interesting problem is right here. Team C pulls with force vector C such that the ring does not move. So this game, there's there's a ring in the very center, and they're trying to pull it into their zone to win. So the situation we have to figure out is, given those other two force vectors in the A and B direction, team C is pulling with such a force that the ring does not move. So it's canceling their net effect out. All right. So a couple things, just in terms of a concept, like what is going on here with the force? Think of it this way. So if you add up vector A, force vector A, and force vector B, C is canceling it out. So what we have to do, because a vector is both magnitude and direction, when we say, we can't just say it's equal to C, we have to say it's equal and opposite. Okay, so it's canceling. A plus B is the opposite of vector C, and that's what's stabilizing the ring here in the middle. Okay, so let's next talk about how the vectors are given to us. These are standard, I should say, linear combinations of the standard unit vector. Whenever you see these I hat and j hat things going on, in class you've always seen me just convert these to component form by using those coefficients as the x and y component, and that certainly works here. So vector B likewise will be -6, 1. Okay, so if you think of, what if this was a set on top of an XY axis here, which I'll just put really faintly in there, okay? It does kind of, I think it definitely looks like if you put the ring right at the origin, excuse me, that you will see that these points make sense. In other words, 5, 2 definitely looks like that point when you compare it with -6, 1 for that point. So we just have to figure out what C is now. So what we're going to do is pop this into play here. Let's just take this down, make the pen a little bigger there. Take this down and fill out what we know about it. So the opposite of the sum of those two vectors has to equate to what vector C turns out to be. Maybe I'll start color coding here. Okay. So A is 5, 2. So I'm going to go 5, 2. And we're combining that with B, which is blue. So that's going to be -6 and 1. So we could actually do that addition on the inside there and come up with 5 and -6. That's going to get you a vector of -1, and then the 2 and the 1 will give you 3. Okay, so -1, 3, and this all, if we take the opposite of that whole thing, we will get vector C. So don't forget, this opposite piece is important. So that'll give us basically 1, -3. You're just, in a real basic way, just multiplying that negative, that scalar. That was one of the first things we talked about this unit way back in January, was scalar multiplication. Okay, so that's what vector C is. So what we have to, is there anything else we have to do now? It says, what is the magnitude of vector C? Okay, well, now that we have vector C, we can definitely calculate its magnitude. We've done that before. That's going to be the square root of the sum of the squares of vector C's components. So you'll get here radical 10, which we're instructed to round off to the nearest tenths. So this is about 3.2. So that is the first question we answer there. Now we have to get into what direction, excuse me, in what direction is team C pulling? Assume 0 degrees is the rightward direction. So we're used to that. 0 is usually pointed due east or the positive x-axis. So keep in mind we are looking for the overall angle between 0 and 360. That's telling us two things. One, we're in degrees. Yay. Two, it needs to be a positive angle. Okay, you can't just say negative, 45 degrees or something like that. You gotta read this angle, this direction angle, as a positive angle between 0 and 360. So we're looking for that green theta that I just wrote on the graph there. But what we're going to have to start with is finding just theta using our formula. Remember, every time we use this formula, it seems we need to kind of unpack or adjust for what quadrant we're in. So we are still using vector C for our x and y components. So as we compute the tan inverse, it'll be tan inverse of -3 over 1. And that angle, let me see if I got a calculator open here. Yep, I'm in degrees, so excuse me. So we'll go to second. Oh, double check our mode first. Yeah, we did that. Second tangent, -3 divided by 1. Okay. So you get this -71.57. -71.57. And since I'm in degrees mode in the calculator, that is a degrees angle, but that's a problem because that's just telling us this angle here. It's not a huge problem because we can replace that answer by adding 360. So if you're at a certain spot on a circle and you don't like the way it reads, it's negative, I need it to be positive. You could just add, in this case add, I mean if you went the other way you would be subtracting, but adding 360 will get us to the exact same spot. It'll just result in, and I suppose I was using green for that now, so it'll just result in a new theta, which is, if you add that together, you get 2, well, and we're supposed to round off to the nearest degree. That's also thrown people off lately. They're reporting tenths and hundredths and getting like a weird, you're close, but it's wrong. So make sure as you add that up, you end up with rounding to the nearest degree, you get 288. Now that is the angle that takes us all the way to vector C.